All right, let us take a look at the following problem. Two systems here, springs in series and springs in parallel. And the question is, what will the effective spring constant be in this case and in this case? And from that, we can calculate the angular velocity, omega. So if we start with that system in series, what we actually have here is if you extend the two springs, here, for example, with if you extend this with delta L here, then there will be an extension delta L1 on that spring and delta L2 on the second spring. And if we are applying a force F here, and hold the system at rest, in that case, there will also be the same force up here, F. And the spring K1 will be having a force like that, down, and the K2 spring will feel force the same, up. So this point is not moving here, and you're applying a force F here. So we know from Hooke's law that F is something like the spring constant times the extension. If we think about this system here, we can say the spring constant, the effective spring constant. And we also have for the springs here, we will have F equal K1 and also K2 delta L2. So what we have here is delta L, that's equal, if you use this equation here, F K effective, and we know delta L, the total delta L, which is extended here, is the sum of delta L1 and delta L2. So which from those equations we get F divided by K1 plus F divided by K2. And this is equivalent to 1 over Kf equal like this. Okay. And here he says, let's check it. If K1 equal K2 equal K, what do you get? So in that case, you would get this. Kf equal 1 over K plus 1 over K. So 2 over K. So that is Kf equal K half. And omega would be Kf over the mass equal k divided by 2m. And this is exactly what you have here. The angular velocity. K over 2m. So, and then we can continue with this, the second system here. So you have instead here two springs in parallel. And if we think that the device here is very stiff, then when you move this down, if you move this system with delta L down, both the springs here will also have to move delta L. So then you get you have again this one effective delta L, but now you get this instead. There will be one force here, F, but here it will be F1 and F2 instead. So if the system is at rest, then F equal F1 plus F2. If it's kept in a static situation. So that's the situation for a parallel case. So you have this just have, but now you have here F1 equal k₁ delta L. And you have F2 equal k₂ delta L. So you see, you can have different forces here, but you have the same extension here and here. Because when you extend this a certain distance, the same will happen to the springs up here. So, okay, from these equations, we have this kf delta L equal k₁ delta L plus k₂ delta L. So this is equivalent to kf equal k₁ plus k₂. So the spring constants are added instead in that situation, and the angular velocity will be kf over m, and if those are equal, so it will be 2k over m. And yeah, 2k over m. So we are done. Thank you very much. See you later.